Here we go with the last part of capacitors. Now, this is the idea of the energy stored in a capacitor and what happens to a capacitor when you put something in between the two plates. All right. The amount of voltage applied to a capacitor will increase the amount of charge. So if we look at the energy, which we know is charge times voltage, as we charge the capacitor, it takes more and more and more energy. And so as we add charge, it takes more energy to add the next one. So if we kind of shrink this delta Q down to a very, very small amount, you'll see that that ends up basically being, for those of you taking calculus, an integral. And it's an integral of a linear function, so it should be fairly easy to do. The integral is basically the amount of energy it takes is going to be the area under this curve. So that's going to be 1/2 the total charge times the voltage. So the amount of work it takes to charge up that capacitor. You have to push the charge onto there. It wants to stay neutral, but if you give it a push, it'll build up that charge. Now, we don't always know charge and voltage. So if we reuse our definition for capacitance, we can replace 1/2 QV squared. We can replace the Q or the delta V. So if we replace Q as C times delta V, you get 1/2 C times delta V squared. Or if we replace the delta V with Q over C, the amount of energy it takes to charge the capacitor is 1/2 Q squared over C. So these three equations here tell you how much energy it takes to charge a capacitor, depending on which two of the three variables you know. All right. A dielectric is a special kind of insulator. It's basically a type of insulator that oppose electric fields. They line up with, they kind of polarize and align with the field. And that basically shrinks the electric fields, because instead of going from positive to negative, you have all these little negatives and positive kind of canceling it out. So you have the electric field that would have been there, but there's going to be an electric field in the opposite direction, which kind of cancels it out somewhat. When we're adding vectors and we're adding two vectors that point in opposite directions, you just subtract them. So that means there's less electric field, so it actually means you can put more charge on there for the same amount of voltage. So if you can put more charge on there for the same amount of voltage, you have more capacity for charge, more capacitance. So each dielectric has a different effect on it. And we're going to use the Greek letter kappa. I know it's kind of annoying, we got more Greek letters, more things, kind of a curvy K. We call that the dielectric constant. It just tells you how strong of a dielectric it is. Going from a vacuum which has a dielectric constant of 1, that's where it doesn't really affect anything at all. And let's just kind of assume anytime I have a 0 here, that means the voltage with no dielectric in the middle. And when I put a dielectric in, I'll get a new voltage. It turns out the new voltage is equal to the old voltage divided by kappa. That means it takes less energy, because with nothing in there, kappa is equal to 1. As we get more and more stronger dielectrics, that amount of dielectric constant is going to shrink the voltage. All right. We're going to call Q0. It'll be the same there unless we're changing things. Then the capacitance goes up by a factor of kappa. For a parallel plate capacitor, we can rewrite that as kappa epsilon 0 A over D. And instead of writing kappa epsilon 0 every time, sometimes we write that the parallel plate capacitor is epsilon A over D, where we know it's no longer, there's no longer a material, there's no longer a vacuum there, there's actually a material. So that epsilon without the 0 tells you there's a material in there. And so the amount of energy is going to, it takes more energy because you can build up, to get to that same capacitance, you can build up more charge. Right, here are a couple of values that we'll be able to see. Air is very, very close to 1 as it's going along there. Water has a very, very high value. Water is a very, very good dielectric until you start dissolving anything into it. So we'll be using these a little bit in class. All right, have a good rest of your weekend.